All right, so we're going to wrap up this last question we were working on yesterday. We were integrating, aka working backwards from these implicit equations where we might have like x's and y's mixed in. And I believe on this number 6, we eventually got to the general solution, like kind of the rough original equation we had, and then we were able to figure out c. Did we get that far? Did we have negative e to the 1/2 power? Okay, but now that we know what c is, we can substitute it back in to figure out the particular solution. So I just want to make sure that we kind of understand what this final solution would look like. So if we take this c value and substitute it back in for c in the general solution or the general equation, we would get something that looks like this. Okay, we're just making that replacement or substitution. If this was some type of free response type question, you could leave your answer like that. Okay, technically you found that original y equation, but if this was a multiple choice type question, it may not look exactly like that. Okay, there is a way that we can simplify what we have a little bit further, and we got to think about kind of our exponent rules. If you're multiplying the same base together, what do you do to the powers? We add them. Okay, so we can rewrite this as negative e to the 1/2 plus negative x to the negative first, but that would just end up being a subtraction if you add that negative. So there's another way you could represent your particular solution or the beginning equation you had. Okay, so free response type question doesn't really matter, okay, but if it was a multiple choice, you may need to rearrange it so your answer matches kind of one of the options that they have. Okay, we got to be familiar with rewriting things, that way we can figure out kind of what's what. Okay, so today, speaking of free response question, we're going to take a look at a sample one from a while ago, okay, 2000, and then we'll take a look at, in my opinion, some simpler equations to work backwards from. We're going to relate it back to particle motion because I think we're getting a good understanding about position, velocity, and acceleration, all those different functions. So let's take a look at this one. Consider the differential equation that is 3x squared over e to the 2y. I know it might be a little vague on your paper. We're going to find the solution. We're going to go ahead and skip part B. I just want to make sure that we can go ahead and figure out the beginning equation we had. So notice how it says find a solution y equals f of x. We know f of x and y are the same thing. I mean, they're setting them equal to each other anyway. But they're giving us a derivative equation and they're asking us to figure out f of x, aka the original equation. So we're going to have to work backwards from the derivative. They also give us a point to use to possibly figure out what that c value is. So let's go ahead and try this one. We have x's and y's mixed in, so let's go ahead and separate the variables. We'll try to get y's on one side, x's on the other. How might you want to try to do that? I'll tell you right now, on the AP exam, if there was a question like this, you would get a full point just for separating the variables. Okay? So it's important that we can get x's on one side, y's on the other. Even though you can't get the right answer in the end, okay, show your work. They'll give you partial credit as long as your work is correct. So if we can separate them, that's a full point. You got 1 out of 9 right there. Okay? Can we separate the variables? What's that? Cross multiply. All right, so we'll have e to the 2y dy equals 3x squared dx. There's a point. If you don't write anything else on that paper, you got 1 point. All right. Now that the variables are separate, we'll go ahead and integrate both sides. How might you want to work backwards from e to the 2y? What do you think, Dan?
Well, we know that the derivative would just be the original times the derivative of the top, which would be 2. So instead of multiplying by 2, you could just divide by 2.
Okay, so you kind of see that connection.
Yeah.
That would be perfect. So we would have a 1 over 2 e to the 2y. If you wanted to check your work, okay, take the derivative of this. The derivative of e to a power is e to the power, but times the derivative of that power would be 2. Since we have that 1/2 out front, that'll cancel out the multiplication of 2, and that's where that coefficient of 1 comes from. If you can't see that, though, okay, how else could we have worked backwards from e to the 2y? It's either a reverse power rule, like x to a power. It's either the natural log. It's either e to the x or e to the y. This is not just e to the y, it's e to the 2y. Can we think about a technique that we could use to help us work backwards? Yeah?
You could just take we're talking about the right 3x, right?
No, we're still working on this side. I'm saying if I know you saw it, but if some people don't really realize that there should be a 1/2 out front, how else can you work backwards from this? Can we think about a technique or a method to help us work backwards? What's considered the inside of an exponential function? Are we thinking the power, that exponent, maybe 2y? We could try u sub. Okay, let's check this out. If we let u be 2y, the derivative du over dy in this case, because we're working with a y, not an x, would be 2. So if we rewrote the original integral, we'd have the integral of e to the u, and then instead of dy, we would need du over 2. So we got to work backwards from 1/2 e to the u. If we work backwards from e to the u, that's just e to the u, and we have the 1/2 out front. And maybe instead of the u, we'll substitute back in the 2y. Okay, so there's that 1/2 e to the 2y that Dan noticed kind of as a pattern. Okay, but even if you can't recognize it, you could still utilize u substitution, okay, an integration technique. Let's go ahead and work backwards from the right-hand side. I think that's a little simpler for us, right? X to the 3rd plus c. Okay. Again, if this was an AP question, you would have gotten another point for the correct antiderivatives. You would have had to have both of them. So even if you didn't have this one correct and this one was, you would have lost that point, okay? But don't get upset. Just because maybe you didn't get this side correct doesn't mean we can't still go through the problem to help us figure out that original function, because there's still points to be earned. Okay, so even though you make a mistake, if you carry that mistake through, they're not going to penalize you more than once. Does that make sense? Yeah.
Can you explain how you found the antiderivative on the left again?
Okay, so Dan noticed a little pattern here. Do you want to know Dan's pattern or the u substitution? Dan's pattern. Okay, so Dan noticed, he thought in his head, what does he have to take the derivative of to get a 1e to the 2y? If you think about the derivative of an exponential, the derivative is e to that power times the derivative of that power. But if you have just e to the 2y, the derivative would be e to the 2y times 2. Notice how the 2 we can move out front would be a coefficient of 2, but we need a coefficient of 1. So what do we have to multiply this by to turn that 2 into a 1? Would be the 1/2. So that's where that 1/2 is coming from out front. Okay, it's basically taking whatever that value is and dividing it by that coefficient, kind of like a reverse power rule, but we're not adding 1 to the power. So it doesn't work exactly the same. Okay, So you could kind of do process of elimination in your head, or U substitution would work every single time. Okay, let's see if we can go ahead and get the y variable all by itself. Okay, there's another point to be had for that process. So if we can, let's see, if we multiply both sides by 2, that'll get rid of the 1/2. So this would be 2x to the third. And you could write 2c on the end, but 2 times a constant is still a constant, so if you wanted to, you could just leave it as c as well. It doesn't matter. Can we keep going from there? How can we move a base of e to the other side? A natural log. So natural log of 2x to the third plus c. And then we can divide everything by 2, aka multiply by a half, so maybe we'll put a half coefficient out front. All right. So there's our general solution. Even if, I'm going to reiterate it again, even if we were not able to correctly get this antiderivative, okay, let's assume this was wrong. We wrote something else there. If you still solved for y algebraically correct, you would still get another point, even if this is wrong, okay, because you carried your mistake through. So don't get caught up again if you can't figure something out. Just carry that mistake through and you'll be fine. All right, there's our general solution. How can we figure out what c is? There we go. We're going to go ahead and plug in that point, that condition or ordered pair they gave us. So if we plug in 0 for x, we should get 1/2. All right, so we can divide the 1/2 over. We would get a 1 on the other side. And then to get c by itself, we'd have to move the natural log over, but that would become a base of e, and the power would be 1. So our c value is e to the first. You would get another point if you found that correctly. By the way, you would get another point for writing the plus c on the end, just by having that. There's a lot of points to be had in this type of question. Okay? So again, don't forget the plus c, don't forget to separate the variables. If you make a mistake, don't worry about it, just carry it through and you'll be fine. So let's bring everything together. We have the general y equals 1/2 natural log 2x cubed plus c. We'll go ahead and substitute in the value of c that we found. All right, so by my count, okay, this is where I think the points would have been had. You would have got 1 point for separating the variables. You would have got another point for the correct antiderivatives. Both of them, okay, even if you had the x to the third power correct and this one was wrong, you would lose that point. It would have to be both, kind of all or none. You would have got another point for writing the plus c. You would have got another point for solving for y. You would have got another point for finding the c value, aka using that ordered pair. And you would have got the last point for your final function or solution. So I think this is why this particular free response question is only having 2 parts to it. You see A and B at the top. This first part I would think would have 6 points. That means the second part, part B, would only be 3 points. Okay? So in my opinion, we could separate the variables. We may or may not get the correct antiderivatives. we definitely can write on our paper a plus c. Algebraically speaking, we should be able to solve for y, because you're just moving terms to the other side of an equation. You can plug in a point and figure out a value. Again, that's just solving. And you can copy down an answer. So out of all of those, the only question mark is finding the antiderivatives. Okay? So even if you can't get it, follow your mistake through and you should be fine. Do we understand that? Okay, don't give up. Yeah?
If you can't get it and you have a mistake, would it not be a good idea to put something really easy as your mistake, algebraically, to carry down through? Like, say you messed up the antiderivative,
Right.
and you just put 2y as your mistake.
That's fine.
That would be...
That's fine. You would lose that point. But if you carry your mistake through correctly, you wouldn't lose anything else.
Okay.
Okay? Strategy. Okay? Strategy. Because you're showing that you know the calculus, like what needs to be done. The only mistake you made was working backwards. Okay? So they're only going to penalize you that one time. Right? Okay. Strategy. All right. Looks good, guys. Let's take a look at some particle motion examples. These might not necessarily have x's and y's in them, because with particle motion we're normally dealing with t's or a time, like at a specific moment in time. Where is a particle located? What's its velocity? What's its acceleration? So we're still going to be working backwards. It just might not be in the same sense of needing to separate the variables, find an antiderivative, okay? We may not need to do the first step in separating if we don't have those two variables listed, okay? But we still got to figure out antiderivatives, figure out a c value, maybe solve for y. The rest of it's going to continue through. So let's check out the first one. The acceleration of a particle moving along the x-axis, so we're only moving left or right, is given by that function. If the velocity is 25 when t is 3, maybe we'll write that down. We can say v of 3 equals 25. And the position is 10 when t is 1. Find the position x of t. Okay, so maybe our position would be x of 1. They can label the position equation whatever they want. Sometimes we use p of t in here just to identify position, but they're probably using x of t because you're moving across the x-axis. So don't get tripped up because they used a different letter. Okay, it still represents a position equation. So how might we want to go about this? We're given the acceleration equation. We're given some information about velocity and position. How can we, in the end, figure out the position function? Can we think about what we have and what we need to do to get what we want? If you think about the order of your functions. What do you think, Joseph?
Turn it into the velocity function, then the position.
And then the position. Okay, so if we're starting with acceleration, we would have to integrate that. And that result would represent the velocity function. Okay, so let's go ahead and work backwards. Again, there's no separating needed to be done here because we're just working with t's. But we're still working backwards. So if we work backwards, we'll have 3t squared minus 2t plus c. Okay, again, if we work backwards, this is representing the velocity function. So this is a general solution for the velocity. Can we figure out the particular or the exact solution for the velocity function? Do we have any way we can figure out what that c value is?
Plug in the point.
There we go. We're going to plug in that ordered pair or condition they give us. So if we plug in 3, we should get 25. Let's see, 27 minus 6 plus c. C is 4. That work out? Okay, so velocity is 3t squared minus 2t plus 4. Now, since this is a multiple choice question, maybe we can start to take a guess as to what the answer may be. Okay, so if this is the velocity function, we know we would have to work backwards again, okay, integrate this to get the position. Can we think about, if we were to work backwards one more time, what it should start to look like? Do you see one of the 5 options that are starting to take shape? Probably C, right? Notice how they're trying to be a little tricky here. Do you see how B was the exact velocity equation they gave us? Okay, so some of us might get tripped up and notice how, oh, that's on there, that must be it. But they're asking us about position. So we have to integrate one more time. We have to work backwards from that. So if we started to work backwards again, that would be t cubed minus t squared plus 4t plus c. But the only option that has that look to it is letter C. So maybe you don't actually have to figure out that constant on the end. It looks like if we did figure it out, it would be 6. Okay, you could figure it out because they give you the point to help you do that, but since it's multiple choice, it's not really needed. Okay, but if it was a free response, you would definitely have to go through that. All right, so that one was a little tricky because we had to work backwards twice, but hopefully that makes sense, because if we're starting with acceleration and they're asking us about position, that's acceleration's the second derivative or double derivative, so we'd have to work backwards twice. Let's try another one. Okay, another particle example. Particle moves along the x-axis again, left or right. T is greater than 0. Its acceleration is given by 6t plus 6. At what time, or at the time 0, the velocity is -9 and its position is -27. So maybe we'll write down that information. So v of 0 is -9 and p of 0 is -27. If you wanted to use x of 0, you could, because we're moving across the x-axis, kind of like the last example, but they don't really specify, so it's up, you can make it whatever you want. So we have different parts to this one. Find v of t, the velocity particle at any time. How might we want to tackle that first part? Can we think about what we have and what we need to do to get what we need? Yeah.
You can work backwards from the original function.
There we go. We're going to work backwards from that acceleration. So that would be 3t squared plus 6t plus c. And if we work backwards from acceleration, that's representing velocity. So that's a general solution for velocity, but they want the exact. It says find v of t, like the exact solution. So can we figure out what that c value is? Yeah.
If you plug in zeros, all the t values are nullified and you're only left with c, so c must be -9.
C must be -9. Okay, so v of t is 3t squared plus 6t minus 9. Part 1 done. All right, let's see what else we can figure out about this particle. Find the net distance, aka displacement of the particle on the interval from 0 to 2. Basically where it starts at 0 and where it ends at 2, how far did it travel between those two points? What do you want to try?
You can use your calculator to plug the VT equation into an interval of 2 to 0.
There we go. All right, but let's say we didn't have a calculator. We're going to try this old school, because after all, we might not have a calculator all the time. Okay, I think we could do this one without a calculator. So in order to figure out displacement, we're going to go ahead and integrate velocity, which should be easy because we already figured what that was. Okay, the function for velocity. If we work backwards, we'll get t cubed plus 3t squared minus 9t. And we don't need the plus c's because we know the bounds. So first fundamental theorem of calculus, plug in 2, get a number, plug in 0, get a number, subtract those numbers together. Let's see, if we plug in 2, we'll have 8 plus 12 minus 18. So 20 minus 18 is just 2. And if we plug in 0 for all the t's, we'll just get 0. So it looks like our displacement is 2. We're 2 units away from where we started. However, okay, for part C, they want us to figure out the total distance we traveled. So even though we're 2 units away from where we started, maybe we did some backtracking and we did a little bit more of traveling instead of just getting the 2 units away from where we started. How can we figure out total distance on an interval? We'll talk about A, how we can do it on the calculator, and B, how we can do it by hand, because sometimes you might not have a calculator. What do we think?
Absolute value.
It is, okay. So it's very similar to the net distance. We're just going to take the absolute value of that. So this is when you would need a calculator to type that in with the absolute values. Do we know where the absolute values are? Remember what buttons to press? Let's bring up the integral first. We'll do math 9, bounds are 0 to 2. And then in the function part, we want to bring up the absolute value bars and then type in our function for velocity. Math. Okay, so instead of doing math 9, we're going to hit math, scroll over to number, and it should be the first option, ABS, for absolute value. Notice how the little bars should pop up. So we'll go ahead and type in 3x squared plus 6x minus 9. Looks like we get 12. So even though we're only 2 units away from where we started, it actually took us 12 units to get there because we did some backtracking or changing direction. All right, but let's see if we can get that same answer by hand. Okay, we didn't have a calculator to help us out with that. How might we approach this one by hand? What do we have to kind of analyze or figure out or find? What do you think?
That'd be critical points.
Okay, let's find those critical points. And those are representing kind of where you change direction, where your velocity changes positive to negative when you're moving from right and then you change to left. So let's go ahead and find those critical points. Or maybe you want to say turning points in this particular example, because we have this particle that's moving. So if we're finding critical points, we want to set the first derivative equal to 0. Okay, when you're talking about position and velocity and acceleration, we know the first derivative is velocity. So we're going to go ahead and set velocity equal to 0. Can we figure out those specific moments in time where we change direction? Where do you want to go from there to figure out t? Factor out of 3. And we could probably factor further 2 numbers that multiply to -3 but add to 2. Positive 3, -1. So our times where we change direction would be -3 and 1. So we have 2 turning points, but should we consider or take into consideration both of those?
No.
Why not?
It's negative.
It can't have a negative. At the very top, it said t had to be greater than 0. We're only looking kind of in the future of this particle. So we have a turning point at 1. So how can we use that information to help us figure out our total distance?
Should we make one of those trucks, like,
Like to determine increasing or decreasing or whatever? You could. I mean, if you did that, you would be able to determine if you were changing right to left or left to right at this point. But that might not tell us how much we're traveling.
Do two bracket things, but add them together.
Okay, so we have to first figure out how far we traveled from 0 to 1, right? Because our interval is from 0 to 2. We got to first figure out how far we traveled from 0 to 1, and then add how much we travel from 1 to 2. How much we're traveling left plus how much we're traveling right, or whatever the order might be. Okay, so let's go ahead and we'll think about total distance equals how much we travel left, perhaps, plus how much we travel right. How can we figure out how much we travel to the left or to the right? How can we figure out how far we travel from 0 to 1?
integral.
An integral, right, from 0 to 1 of that velocity. And then we'll do an integral from 1 to 2 of that velocity. Now what's nice is we already know what we should have when we work backwards from velocity because we did that in part B when we did the displacement. So we just got to figure out t cubed plus 3t squared minus 9t from 0 to 1. And then we'll add t cubed plus 3t squared minus 9t from 1 to 2. Make sure we have those absolute value bars, and then we'll be good to go. Okay, so first fundamental theorem of calculus, plug in the top, get a number, plug in the bottom, get a number, we'll subtract them together. So our first distance we're traveling from 0 to 1. Let's see, if we plug in 1 for all those, we'll get -5. If we plug in 0, it's going to be 0, so we're just left with -5. And then let's check out the next one. If we plug in 2 for everything, we get 2. And if we plug in 1 for everything, we said we get -5. And we got to subtract those. So on the interval from 0 to 1, we traveled a distance of 5. And on the interval from 1 to 2, we traveled a distance of 7. So overall distance would be 12. Notice how we get the same thing. So it's a little tedious by hand because you have to figure out where it exactly changes direction and then analyze those separate integrals, how far it travels before the turning point and then after the turning point. Calculator is nice because we just type it in and we're good to go. Okay, but realize we got to analyze where we change direction to figure out that total distance. Okay? How are we doing with working backwards still? Integration? We're getting the hang of it? Hopefully? Okay. We're going to stop there for today. Next week, we're going to take a look at the next section, which are slope fields. This is probably one of my favorite things we cover all year, and I think you guys are going to like it too. So I'm super excited for Monday. Okay. Has anyone taken, what's it called? Not weather. What's the science of weather? Meteorology. Meteorology or something like that with Mr. Adams? You're taking it this year. Did you look at like wind direction graphs? This is going to look very similar to that. So you might be ahead of the game, okay? But it's one of my favorite things. We're going to do it on Monday.
Yeah.
Yes.